Question 13. The table shows the first 5 terms of sequences A, B, and C. Sequence A, we are seeing 5, 12, 31, 68, 129. Sequence B, we are seeing this. Sequence C, we have this one here. Now complete the table to show the nth term of each sequence. Now, the easiest one here to do first is going to be sequence C. So let's look at sequence C. Now, when you look at C, we are multiplying by 2. So times 2 times this one by 2, you get times 2, you get this times 2, you get that. So since there is what we call a common ratio, in other words, when you get 8 divided by 4, you get a 2. 16 divided by 8, 32 divided by 16, you get a 2. 64 divided by 32, you get a 2. So that's a common ratio. So that is what we call a geometric sequence or progression. Okay, so the nth term here is given by AR n minus 1. Okay, AR to the power of n minus 1. Why is it like that? Because if I get the first term, if it is A, then the second term shall be equivalent to AR, because I'm multiplying with the common ratio. The common ratio is the R. Then the third term, I get the second one times, so that is times R, so it will be squared. Then the fourth term will also be that AR squared, then times R, which is cubed. So that means the nth term can be, A is common, it's all written all through, but you can see 4 to 3, 3 to 2, 2 to the 1 here. Do you see that they are reducing by 1? That means I will have R here, then n minus 1. So that's why I have something like this here. Now, we are going to have our A is the first term. So A, let me write these ones very well. This is the first term. And this one here is the common ratio. So our nth term here is going to be, the first term is a 4, then times the common ratio. Just get 8 divided by 4, or 16 divided by 4, which is a 2, then power n minus 1. So I can simplify this. 4 can be written as a power of 2. So we can have 2 squared times 2, then power n minus 1. And then I can add these ones using rules of indices, 2 plus n minus 1. And that will be 2 power n, then plus 1. Because 2 minus 1 is a 1. So that is what I have here. Here I will have 2 to the power of n plus 1. Okay. Alternatively, I can have something like this. I can have positions. Position 1, 2, 3, 4, 5 positions of the terms. I can let this one to be the position n. Then we have the terms. But when you look at these terms, I have the 4. I can write all of these ones as powers of 2. So 4 is 2 times 2. I mean 2 power 2. Then 8 is 2 power 3. We have 3, I mean the third term 16 is 2 power 4. 2 power 4. Then this one is 2 power 5. Then 5 here is 2 power. I mean this fifth term 64 is 2 power 6. Now ask yourself what was done to the positions, because what is changing are the powers. So connect the powers to the positions. Okay, so when we connect them to the positions, you can see that they are adding 1 here. 1 plus 1, you get the 2. 2 plus 1, you get the 3. 3 plus 1, you get that 4. 4 plus 1, you get that 5. 5 plus 1, you get that 6. So meaning the nth term is going to be, so nth term is going to be equal to 2, then power. The position here is n, but then they are adding 1. So plus 1. So that is what you're having here. Then the next one, sequence B. It's a linear sequence. Sequence B. Now, since this one is linear, because you can see that here, they are adding 1. They are adding 1 in the denominators, but they are subtracting 1 from the numerators. This is linear up and linear down. Okay. Now, if we look at the numerators, numerator. So what happens on the numerator? Nth term, of course, is going to be equal to a, then plus n minus 1d. Why are we having this one? In fact, this one, we call it arithmetic progression. This is geometric when you're multiplying. So if you're adding something or you're subtracting something, that is arithmetic. Arithmetic progressions or sequence. Let me maintain the word sequence. So if the first term is a, first term, then the second term, we are adding a common ratio there. So I mean a common difference, we call it a difference. So plus a d. Then the third, this one we have gotten plus a d. So a plus d, that will be 2d. Then again add a d here. You will get a plus now 3d. And then that means the nth term is going to be equal to, a is everywhere, then plus. But you see 4 to 3, 3 to 2, 2 to 1 here. So it is reducing by 1. So I will say n minus 1. This term here, fourth. So this term, then minus 1, then times the d. That's why we have this one here. Okay. Now, the nth term. So a here is the first term. Then this one here is the common difference. Okay, so for the numerator, we are going to have our a, the first one, that is 10, then plus n minus 1. Our d is the common difference. We are subtracting a 1, so put here negative 1. Now open the brackets, 10 minus n plus 1, because the negative affects everything here. 10 plus 1, you will get 11, then minus n. 11 minus n, that is for the numerator. Then, how about the denominator? So we shall have the same thing. The nth term is going to be equal to our a, for the denominator is 3, then plus n minus 1. The common difference is a plus 1, so times 1. In other words, you're having 3 plus n minus 1. And you have here n, then plus 2. So this will be n plus 2 as the denominator. Sequence A. What do we see on A here? This is 129. We can have a cube number here. If this is n. Okay. If this is our n here, 1, 2, 3, and both. Now suppose I have n cubed. 1 cubed will be 1, 2 cubed will be 8, 3 cubed will be 27, 4 cubed will be 64, 5 cubed will be 125. But do you see that 125 plus 4 gives us 129? Also here, if I get this one plus 4, also this one, when I add a 4, I get the same thing. You see that? I get the same thing. So this means we are going to have n cubed, then plus 4. That will be the nth term. Okay? So this will be n cubed plus 4. That is what you have there. My space here is done, but I think that is that.